Here's where we're going. First, we'll meet the delete command. What apoptosis is, why evolution installed it, and how it actually runs in a cell. Then we'll look at how cells listen to tiny signals, chemical sparks, ion flows, redox shifts, and why small nudges can trigger big pathways. After that, we'll map the frequency soup we live in. Power lines, Wi-Fi, 4G per 5G, Bluetooth, chargers, all with simple ranges and how fast energy drops with distance. Then we'll cross the bridge where this story lives. Oxidative stress. That's where reactive oxygen species, ROS, can flip from helpful messages to harmful noise that pushes cells toward delete. From there, we go to evidence. In vitro cell studies, animal work, and human data, you'll hear the mainstream stance. Non-ionizing radio frequency doesn't have enough energy to break DNA directly. You'll also see papers reporting increased RAWs, calcium shifts, or apoptosis markers under certain exposures. We'll separate what's been replicated from what hasn't, and we'll call out limits like heating confounds and cell line quirks. We'll also give the guardian of the genome his scene, P53 deciding repair or remove. Then we'll stress test the claim with dose, distance, modulation, and the weird window effects where biology reacts at specific ranges. Finally, we land on practical steps that lower baseline stress without panic or snake oil. Rules of the game. Facts first, hype never. Ionizing versus non-ionizing matters. If a study is disputed, we say so. If a mechanism is a theory, we label it. Our method is simple. Cause. Signal, pathway, outcome. If that chain breaks anywhere, we don't sell it. Cool? All right, load the delete command. The delete command, Apoptosis 101. Imagine a city that fixes itself by quietly removing broken buildings before they collapse. That's your body. Apoptosis is the permit system and the demolition crew. Evolution put it there to shape you in the womb, prune your immune cells, and keep would-be cancers from taking off. Without it, fingers fuse, immune cells attack the wrong targets, and damaged cells linger until they cause bigger problems. With too much of it, you lose neurons, muscle, and organ function, so the body keeps it tight. Here's how the delete runs. Inside each cell, there's a set of proteases called caspases. Think of them as scissors that only cut when someone removes the safety cap. The intrinsic pathway starts at the mitochondria, the cell's power stations, and weirdly also its executioners. When a cell senses serious trouble, like heavy DNA damage, major oxidative stress, or messed up proteins, the outer mitochondrial membrane gets more permeable. That's controlled by the BCA2 family, the bouncers at the door. Some members are pro-def, like BAX and BAC. Others are anti-def, like BCA2 and BCA-XL. When the pro-def side wins, mitochondria leak cytochrome C. That's the signal that assembles the apoptosome, which activates caspase 9, which then flips on executioner caspases 3 and 7. Those chopped structural proteins cleave a break called ICAD and unleash CAD, the nuclease that ladders DNA into neat fragments. It's disturbingly tidy. There's also the extrinsic pathway. That's when a cell gets a kill order from outside. Def receptors like FAS or TNF on the membrane bind their ligands. That pulls together disc complexes, which activate caspase 8, and the scissors party starts. In many cells, both routes meet up at the mitochondria, because caspase 8 can activate BID, which tips BAX back toward pore formation. The routes are different doors to the same end. Who decides which door opens? Enter P53, often called the guardian of the genome. It's a transcription factor that wakes up when DNA is hurt. Double strand breaks, weird replication stress, or oxidative lesions. Stabilized P53 pauses the cell cycle and buys time for repair. If the damage is fixable, repair teams patch it and P53 stands down. If not, P53 tilts the BCL2 balance by upregulating pro-death proteins like PUMA and NOXA, and the mitochondria open up. So, in a very real way, P53 is the judge that reads the file and says repair or delete. Now, what trips the alarms in the first place? Plenty of normal stuff. Cells constantly deal with reactive oxygen species. They're not just bad, they're signaled. A short pulse of ROS can nudge pathways to adapt, grow, or defend. But if ROS builds up beyond what antioxidants like SOD, catalase, and glutathione can buffer, it damages lipids, proteins, and DNA bases. Markers like 8-OEGG pop up, and damage sensors engage. Misfolded proteins, ER stress, calcium overload, and persistent inflammation all feed into the same decision tree. The point is, the delete command isn't random. It listens to context. This is important for our central question. If chemistry speaks the language of charges, electrons, and ions, then physical fields might whisper in that same language. Membranes have voltages. Channels open and close with tiny changes in electric potential. Calcium influx can set off huge cascades. Mitochondria run on an electrochemical gradient. So in theory, very small physical nudges could, under the right conditions, move a cell from fix it to end it. That doesn't mean every nudge does. It means the system is responsive by design. There's also the Goldilocks idea, called hormesis. Small, short stress can be useful. It trains the response systems like exercise does for muscles. Big or chronic stress breaks things. With apoptosis, a modest redox pulse might help clear out the most damaged cells and keep a tissue healthy. Too much redox chaos or the wrong cells at the wrong time, think neurons, and you get degeneration. That's why the stakes here cut both ways. Too little delete invites tumors. Too much delete thins tissues and brains. Let's zoom into the details the body uses to keep this precise. The caspase cascade is nonlinear. Once a threshold is crossed, it goes fast, which is why timing matters. Mitochondrial membrane potential, basically how charged that inner membrane is, can wobble when a cell is stressed. A drop there makes cytochrome C release more likely. BCL2 family proteins respond to dozens of upstream cues. DNA damage markers like ATM, ATR, oxidative shifts, cytokines, and calcium spikes. Death receptors are kept in check until ligands arrive from immune cells that have vetted a target. It's layers of brakes and gas pedals, not a single on-off switch. And then there's cleanup. Apoptotic cells flip phosphatidylserine to the outer surface and eat me flag. Neighboring cells and macrophages recognize it and swallow the debris quietly. No mess, no inflammation, no alarms to the whole tissue. That's a huge difference from necrosis, which spills guts and triggers inflammation. Your body prefers quiet deletions. So yes, there is a delete key. It exists to keep you alive, not to betray you. It sits inside a network that checks damage, balances signals, and acts when the cost of repair is higher than the cost of removal. Our job now is to ask a sober question. Can modern signals, non-ionizing fields from everyday tech, meaningfully tilt the inputs to that decision? Not by smashing bonds like X-rays do, but by nudging the redox and calcium dials that mitochondria and P53 read. We'll get there. First, a quick look at how cells act like antennas, how tiny pushes become big choices. Because if a whisper can change a verdict, we should know how the courtroom hears. Signals in cells, how little pushes make big changes. Have you ever wondered why a tiny spark can start a whole fireworks show inside a cell? Cells are electrical, not just kind of. The membrane around each cell holds a voltage, like a charged battery. On one side, more positive ions, on the other, more negative. That separation is energy, and it runs the gates. Proteins that open and close to let ions like sodium, potassium, and especially calcium slip through. A few thousand ions move, and suddenly enzymes wake up, genes switch on, Mitochondria speed up or slow down, small push, big ripple. Calcium is the star of this whisper becomes a shout story. Resting calcium inside a cell is tiny, nanomolar low. A brief pulse all by itself can flip whole pathways. It binds to commodulin, which flips on kinases like CAMKI. That changes which proteins get phosphorylated, which changes what they do. It also talks to the nucleus. Transcription factors respond. And now the cell is making different tools for the next hour, the next day. And because calcium also hits mitochondria, it tunes energy output. And if it floods, leans towards stress and even the apoptotic machinery. That's why researchers care so much about anything that might nudge calcium channels, especially the voltage-gated ones on the membrane. Now let's talk redox, the chemistry of electrons and oxygen. We throw raws around like it's a villain, but honestly, it's more like a text message. Low, short pulses of reactive oxygen species carry info. They tweak cysteine switches on proteins, modulate signaling, and prime defenses. Antioxidants aren't there to erase all raws. They're there to keep the message short and clear. When production outruns clean up, think too many texts at 3 a.m., the messages turn into noise. Lipids oxidize, proteins misfold, DNA bases take hits, and stress alarms trip. Markers like 8, OHG tell you the messages went off the rails. So how do tiny pushes get past the membrane? Mechanosensitive and voltage-gated channels feel changes in stretch and charge. Receptors bind ligands and start cascades that amplify with every step. One receptor activates 10G proteins, which activate 100 enzymes, which make thousands of second messengers. That's built-in gain. It's why biology can react to whispers without cooking itself. And it's why non-thermal stimuli, signals that don't heat tissue measurably, are still a scientific question. If the gate responds to a charge change, you don't need a furnace, you need the right nudge at the right time. This is where windows come in. Cells don't respond linearly to everything. Sometimes there's a sweet spot. Too weak and nothing happens. Too strong and systems clamp down. Hormesis lives here. Small stress sharpens responses. Exercise is a perfect example. A bit of damage, a bit of ROS, then the rebound makes you stronger. But keep pushing past recovery and you get injury, not growth. Cells use the same trick. Short redox pulses train antioxidant defenses. Chronic overload depletes them. And now the same cue that used to help flips toward harm. Let's make it concrete. Voltage-gated calcium channels open with small changes in membrane potential. If a stimulus, chemical or physical, leans the voltage a few millivolts toward opening, you get more calcium spikes. That elevates mitochondrial work, which makes more RAWs as a byproduct. If antioxidant systems match that rise, you adapt and get tougher. If they don't, RAWs lingers, tweaks P53 stabilization, and the damage versus repair math shifts. Same initial nudge, different context, very different outcome. That's the knife edge the cell walks every day. Mitochondria sit at the pivot. They read calcium and redox in real time and adjust ATP output. But their inner membrane potential, the charge across it, is fragile. A drop makes it easier to release cytochrome C when other signals say, it's time. That doesn't mean a little wobble equals doom. It means the system sums inputs. DNA damage signals from ATM, ATR, cytokine noise from neighbors, calcium pulses, ROS tone. The final vote decides whether to pause and fix or call in the caspases. Could it be that physical fields nudge the same levers chemistry does? That's the open question. We know cells are antennas for ions in charge. We know small pattern inputs can flip big pathways. We also know most safety standards focus on heating, not on narrow windows where non-thermal nudges might matter. So we test, we look for consistent cause, signal, pathway, outcome chains. No chain, no claim. Next, let's map the frequencies actually around us and how strong they are so we can see which nudges are even plausible in real life. The frequency soup we swim in. Let's map the noise we actually live in so we're not arguing with ghosts. Start at the slow end. Power. The stuff in your walls hums at 50 or 60 hertz. Big motors, power lines, induction cooktops, all in the extremely low frequency, ELF, band, wavelengths the size of cities, fields that rise when current flows, and they fall fast with distance. A step back matters. Slide up to kilohertz and megahertz. Old school AM and FM sit here, plus some baby monitors and walkie-talkies. Then the modern daily drivers, radio frequency and microwave. Wi-Fi runs at 2.4 and 5 gigahertz, sometimes 6 in newer routers. Bluetooth hangs out near 2.4 as well, but uses tiny bursts and low power. Your phone does 4G around 700 megahertz up to a few gigahertz depending on the band, and 5G adds more lanes. Sub 6 gigahertz like 3.5, and in some cities, millimeter wave up around 24 to 39 gigahertz for short hops. Now, strength. Picture a flashlight. Close up, it's bright. Move away, it fades fast. That's the inverse square law in practice. Double the distance, quarter the power density. Phones near your head, higher local exposure. Phone on a table, big drop. Routers across the room, even bigger drop. Chargers and wireless pads, they use near-field coupling at lower frequencies for a few centimeters. Beyond that, they fall off a cliff. That's why distance remains the cheapest shield on Earth. Near field versus far field matters. Within about a wavelength or two of an antenna, fields can be messy. Electric and magnetic parts don't travel together yet. They wrap around the source. Past that, they lock into a wave and spread predictably. At 2.4 gigahertz, a wavelength is roughly 12.5 centimeters. So your body is usually in the far field for room-to-room Wi-Fi, but in the near field for a phone pressed to your ear or a watch on your wrist. Tiny changes in where you hold a device can change exposure more than any sticker ever will. Let's clear the big physics line. Ionizing versus non-ionizing. Ionizing radiation, UV, X-rays, gamma, carries enough punch per photon to rip electrons off molecules, break bonds directly, and write damage into DNA on contact. That's not what phones and Wi-Fi emit. Radio frequency and microwave bands are non-ionizing. A single photon that doesn't have the energy to snap a bond. The established boring mechanism at these frequencies is heating. Energy absorbed by tissue turns into a tiny temperature rise. That's why safety standards like IC-NIRP and IEEE base limits on specific absorption rate, SAR, and tissue heating thresholds with big safety margins. So why the debate? Because biology isn't just a bag of water. Cells run on charges and timers. Some studies report effects at levels below significant heating, shifts in calcium handling, reactive oxygen species, or stress proteins, while many others don't. That's the non-thermal effects conversation. Standards today say protect against heating, and you're good. Critics say, what if certain patterns, pulses, modulations, duty cycles, matter more than average power? Think of it like sun through blinds. Same sunlight, different flicker on your eyes. Let's talk numbers without drowning. A phone by your head can hit a SAR up to 1 to 2 watts per kilogram in a small region. But that's tested under worst case, continuous transmission. Real calls hop and rest. A Wi-Fi router across the room, power densities in the microwatts per square meter range for most homes, which is orders of magnitude below heating thresholds. Millimeter wave 5G, it doesn't dive deep.